Welcome to Chapter 5 on decimals. Now, decimals is just another way to write a fraction, which is a portion that's less than 1. A decimal is, because it has deci in it, that's part of our base 10 system. So every decimal point is a multiple of 10, just like it is when we're talking about our larger numbers going to the left of our decimal point. We have our ones, our tens, our hundreds, our thousands, our 10,000s, etc. We have the same thing going in the reverse order. But that first digit is not going to be ones, because ones mean I have a solid of something. This is broken into pieces. So this first decimal spot is called tenths. So that's when I break a hole into 10 even slots, how many do I have? And then it's hundredths and thousandths and 10,000ths. And it continues on that direction. That's when you spit on your neighbor, because the words to the right of the decimal place always end in THS. That's how you know that you are talking about the decimal side to the right of the decimal point, and that's the left. This first number has 2 decimal places because we have 2 digits to the right of the decimal point. Now, one of the things that we're going to be doing today, just to get us used to some decimals, is seeing how does a decimal relate to a fraction. So I'm going to write the decimal, which is the same thing as a fraction, it's just written in a different form. We're going to change it over and write it in that form of a fraction. So this is how that's done. We see that we have a number 0.73. You may have a 0 in front of the decimal point. It doesn't matter, you don't need it there. Those in Science City like to put the 0 in front to make sure that we clearly see that there's nothing in front, no whole portion. But in math land, we get a little lazy and we say, hey, if it's not there, it's not there. So this is how we do it. We look into, we say, how many decimal positions do we have? And we would say, oh, well, there's 1, 2 of them. So we keep that in mind. Now what I'm going to do is I'm going to put this number without the decimal point, and that's going to become the numerator, or the top number of my fraction. Now on the bottom, because these are tenths and hundredths and thousands and 10,000s, it's always going to begin with a 1 on the bottom. So I start with a 1. And now I need to know, okay, well, which position do I have? Now I can memorize all of those positions and say, oh, well, this is 2 spots, that's tenths, and this is hundredths. And so to say hundredths, I need to have 100. But in case we forget that, this is how I do it. How many decimal spots do we have? 2 of them. That's how many zeros I have after my 1. And of course, we reduce our fraction if possible. Let's do another one. What if I had a whole number in front? So this is 12.2469. Once again, I start off by putting this whole number as it is, this entire number, without the decimal point, and that's going to be my numerator. So I have 1, 2, 2, 4, 6, 9 as my top number. On the bottom, I start with a 1, and then I need to find out how many zeros would go after that. I count decimal places. Decimal places, once again, are only the numbers to the right of the decimal point. So it's 1, 2, 3, 4. So that's how many zeros I put after. Oh, what if it's negative? Negative doesn't matter. You just keep the negative going along with it in your problem. Same thing occurs. I put this whole number as it is, the entire number, as it is, as my numerator. Get rid of the decimal point. That gets part of the fraction. And then it's over 1, and how many decimal places do we have on this one? Just 1 spot, so only 1 0. Remember, I prefer improper fractions over mixed numbers. I like it if the top is heavier than the bottom, as long as your fraction is reduced. Okay. Why do I prefer that over mixed numbers? We do not use mixed numbers in algebra. And we want to start practicing that now, getting in that mindset that improper fractions are okay, because that's what we're going to be using in the algebra class. So we're preparing ourselves. Now you notice that all 3 of these I didn't reduce. Well, this is the nice thing. This is kind of a neat little thing about these numbers. I can tell straight off the bat whether I can reduce these or not. And this is why. The denominators are all multiples of 10. 10 times 10 is 100. 100 times another 10 would be 1,000, times another 10 is 10,000. So they're all multiples of 10. If you remember from what we did last week in finding our LCMs, those least common multiples, we did little factor trees to break things down into prime factorizations to help us find out the numbers so that we could build up a common denominator. Well, if I have 100, that's just 10 times 10. And every 10 is a 2 and a 5. So even if I had 1,000, well, I just have another 10 here, which would just be another 2 and 5. So essentially what happens is all of these denominators are broken down into 2s and 5s for the prime factorization. Now that's kind of neat because we know about divisibility. Oh, divisibility. How do we know if a number is divisible by 2? Well, we said last week that a number is divisible by 2 if it's even, which means that the last digit has to end in 0, 2, 4, 6, or 8. But since one of my factors is also 5, I need to know how my numbers are divisible by 5. And those were the fun ones because we learned how to count by 5s. 5, 10, 15, 20, 25, 30, 35, 40. It always ended in a 5 or a 0. So it's divisible by 5 if it ends in a 0 or a 5. Well, the nice thing is 0 shares. Okay. So all of these numbers, if it's divisible by 0, 2, 4, 6, 8, or 5, so if your number ends in any of those, if your number ends in any of those, or if it ends in 5, then you can reduce it. If your top number does not end in 0, 2, 4, 6, 8, or 5, you can't reduce it. 3 is not on that list. 9 is not on the list. Neither is 1. That's how I know I can't simplify those fractions any further. Okay? So once again, you know you can reduce your fraction. Okay? Convert your decimal over, put your decimal number over the 100 or the 10,000 or the 1 and the zeros, and then look at this last digit. If this last digit is 2, 4, 6, 8, 0, or 5, you can reduce it. If it's 1, 3, 7, or 9, you can't. And that's how you convert your decimals to fractions and then reduce. For adding and subtracting decimals, before we're actually going to add and subtract decimals, I just want to think about for a moment how we add our regular whole numbers. What did we do in week 1? And if you recall, with adding something like 22, 431, and 9, we would line those up. And we'd say, oh, well, we have 22 plus 431 plus 9. And the question I have for you is, why are they always flush to the right? Why did we put all of these numbers so that they're flush to the right? And the reason for that is so that we're adding the like types of numbers. This last digit, it represents the ones column. This is the ones column. This is the ones column. We're adding single digits to single digits. These both represent tens of things. So this isn't really 2, it's the number 20. And this isn't 3, it's 30. So we were representing all of the tens. And then the same thing for every column over. This would be all of your hundreds, all of your thousands, etc. That's why we all lined it up flush to the right. And then you proceed to add from the right to the left, because if you needed to carry, you could do that. We've got a 10 plus 2 is a 12, and you carry the 1. You've got 6, and you've got 4. So you added up your total to get 462. Okay, does that make sense? We add up all their like columns. But what else do we know about these numbers? Well, now we're getting into decimals. We know that at the end of every number would be a decimal point. That would separate the whole number portions from the fraction portion, which is what the decimal represents. So really, there's a decimal point here, and then you would have possibly more digits to the right. We're going to keep that in mind when we are adding our decimal numbers. If we have two decimal numbers like I have on the board here, 27.23, and we're adding 41.985, if we were to add those flush right, like we did on the last problem, we wouldn't be adding like digits. Because remember, the 7 here are ones, but the 9, since it's to the right of the decimal point, that's tenths. I can't add whole things to a portion. So that's not right at all. That is not how we add up our decimal numbers. We're going to add them up by lining up the decimal points. Make sure that you write nice and neatly to make sure that every column you can clearly see top to bottom, every digit that's in that column. And now we once again will add from the right to the left like we did in the past. Here we're adding 5 to nothing. We could put in 100 zeros here if we wanted to. At the end of decimals, it's just zeros. We don't need 100 of them, obviously, but if you want to see that extra digit to make sure that every spot has a number, feel free to fill it in with a 0. And now we add. We have our 5, 8 and 3 is 11. You put the 1 and you carry 1. That gives us 12. You write the 2, carry the 1, bring the decimal point straight down. 7, 8, 9, nothing to carry there. And add your 4 and 2. So adding decimals, you need to remember to line up your decimal points. And then you do your normal adding right to left. Let's try one more, just to make sure that we have the setup correct. Here we have 3 different decimal numbers, once again being added up. We know we need to line up our decimal points, so we start off with our 732.106. Notice that I make sure that my numbers are well spaced so I can line them up, especially with the digit 1, which is very narrow. It's very easy to put 2 digits too close together and then hard to line up your next numbers underneath them. So make sure that you give yourself enough space to line things up. Then I have 2 digits in my decimal point. And then I have 93. Now I have to be very careful with the 93. 93 doesn't appear to have a decimal in it, but every number has a decimal point. Because we're in the decimal system, it has to have the decimal point someplace. You need to make sure that you line this up correctly. Students like to line this up flush right, because when in doubt, we line up flush right. That's not correct. Where is the decimal point in whole numbers? The decimal point is at the end. So there's your decimal point. Make sure that you line your number up accordingly. That's going to be 93. If you want to put in some zeros as filler, that's fine. You can always add zeros to the right of a decimal point. It does not change the value. And now we have it all set up, we can add from our right to our left, as we normally do. To get our final answer. So remember, if you have a whole number, there's a decimal point at the end. Make sure that you line it up correctly. Subtracting decimals is not any different than adding decimals, but we do need to remember our rules about subtracting. So here we have 2 numbers that we're subtracting. I lined up the decimal points nicely, kept all of my numbers in nice columns to the left and to the right, and now I'm going to subtract. Now here's a problem that students have. Oh, I have nothing up here, so I bring the 1 down. That's not correct. You didn't actually do a subtraction. Remember that space up here means that there's a 0 here. I cannot take 1 away from nothing. So in this case, we have to go over and borrow. So I go from the 2 and borrow, say, neighbor, neighbor, I need a cup of sugar. The 2 decreases by 1. This is still a multiple of 10, so the same rules apply that we had on the left side of our decimal point as when we had the right side of the decimal point. So this 0 becomes a 10. And now I can take 10 and subtract 1 and get 9. 1 minus 0 is 1. I cannot take 9 from 6, so the 6 once again has to borrow. And it's okay to borrow across the decimal point. There's nothing wrong with that. So this 1 becomes a 0, and the 6 becomes a 16 because you add 10 to it. Remember, this is the 10th spot. So from the whole, we broke that into 10 little spots and then added it to the 6 that were already there to get 16. 16 minus 9, it's fun to take teen numbers and subtract 9 because in order to get the right answer, you just add the 2 digits here. 16 minus 9 is 1 plus 6, or 7. Oh, neat little trick. Bring the decimal point down. I cannot take 8 from nothing, so the 0 has to go and borrow. The 5 becomes a 4. The 0 becomes a 10. 10 minus 8 is 2. I cannot take 7 from 4, so I have to go and borrow again. The 4 becomes a 14. Now we can subtract 7 and get 7. And our last one is 3 minus 2, which is 1, to get us our final answer with subtraction. Let's try one more. Here's another example that might mess with us if we're not paying attention to our fine details. In this problem we have 32 and we're taking away 17.84. It's very hard to do mathematics horizontally when you're adding and subtracting. I always like to set them up vertically so I make sure that I'm lining up my correct units. So I put down my 32. Now I remember that 32 is 32 with a decimal point at the end. All whole numbers have the decimal point at the end. And I'm subtracting 17.84. Now, once again, in order to do my subtraction, I do not just bring digits down that are in the second line because I'm subtracting and I'm subtracting them from nothing. I can't take 4 from nothing, so I have to borrow. Now this 0 goes over, but the neighbor doesn't have anything either. So that neighbor has to go over and borrow. So this neighbor goes and borrows from the 2, makes this a 1. That makes this guy a 10. Now that he's got 10 of things instead of nothing, this 0 can borrow from him. So this 10 drops down to a 9. And the final 0 becomes your 10. 10 minus 4 is 6. 9 minus 8 is 1. Decimal point, decimal point, decimal point. Can't take 7 from 1, so I have to go and borrow again. 11 minus 7, though, is 4. And 2 minus 1 is 1, to get your final answer of 14.16. So whenever you are adding or subtracting decimals, line up your decimal point. Make sure that you do the actual operation that you subtract every column. If you need to, fill in zeros for your placeholders. Even though our numbers are decimals, we have the same types of applications to them as we do to our regular positive and negative whole numbers, the integers. So let's review something that's very important for us to comprehend this week and going forward, combining like terms. Now we need to remember that like terms mean that we have terms, the stuff that's being added or subtracted, that have the same variables, and the variables are raised to the same exponents. So up here in my example, I have 6 different terms. Remember, terms are the stuff that's separated by either addition or subtraction. The other thing we need to remember is that the sign in front of the term goes with the term. So in this problem, we see that our 6 terms, we have our 14.5h, then we have a subtraction sign, so this term ends. The next term is a negative 32.79j, then we have a negative 7, then we have a negative 6.7h, we have a positive 17.24j, and we finish with a negative 22.63. Now the terms are being added or subtracted. So we find out, okay, we want to combine any of the like terms. So we look for the same variables, being raised to the same exponents. Now nicely, we're not dealing with a whole lot of exponents quite yet, but I do want to remind us that that is part of a like term. But in this week, we're just dealing with some different letters. Here we have H's and J's. We always start alphabetically, and you put your terms with the variables first, and the terms that don't have variables at the end. And we do it alphabetically. So I'm going to start off, and I'm finding all of my terms that have an H in it. Here's 14.5H. Here's another H, but we need to remember the sign in front of the term goes with the term. So that means that this 6.7H is a negative. So I have a positive 14.5 and I have a negative 6.7. Because all these terms are just being glued together of adding and subtracting, we still have that same concept to it in which we're adding these terms. That's what you can do. That's why we're looking for like terms. We only add or subtract like terms. So I have 14.5 and I'm taking away, or I'm adding a negative 6.7. Well, one's positive, one's negative. That means that we subtract the two. I can't take 7 from 5, so I'm going to have to borrow. 13 minus 6 is 7. My 14 was positive, and that's the larger number, so my answer will be positive. But don't forget the letter. So I'm now going to erase my work and say, okay, that's going to be 7.8H. And now we go through and say, okay, where are my terms with the J? Here's a J. Remember the sign in front goes, so it's a negative 32.79. And over here I have a positive 17.24. Once again, I have one of each sign. One's positive and one's negative. When we're adding like terms with opposite signs, we subtract the number and keep the sign of the larger. Larger meaning, hey, if I subtract this, do I go 17 minus 32, or do I go 32 minus 17? We start with the 32, and we subtract the 17.24. The 32 was negative, so my answer is going to be negative. So I'm just going to put the subtraction sign right there, because I know that that's what my answer is going to be. And now I just have to worry about my subtracting. We always subtract a smaller number from a larger number. The result might be negative because we started with a negative, but we don't put the 17 on top and try to take 32 away from it. We always start with the larger number on top. So now we subtract, and we have a 5 and another 5 and a decimal. I can't take 7 from 2, so I have to go and borrow. 12 minus 7 is another 5. So we have 15.55. J, don't forget your variable. It doesn't go away. We can add these together because they both have a J. It still is going to have a J at the end. And then finally, we look for all the constant values. Those are the ones without the variable. And here we have a negative 7, and at the end we have a negative 22.63. Both of these have the same sign. They're both negative. When we're adding two numbers that have the same sign, you add the numbers and keep the sign. So this is still going to be negative, so I'm going to put that right in. And now I have to deal with 7 and 22.63. Remember, we're adding. That means we have to line up our decimal point. The 7 has a decimal at the end. So I would be taking my 22.63 and adding 7 and line that 7 up underneath the 2. If you need to fill in zeros to remind yourself that that means the same thing, go for it. And now we are adding these, and we can get our 29.63. Once again, these were both negative, so our answer is more negative. We cannot go any further because I cannot combine a term with an H with a term with a J with a term that doesn't have a letter at all, because that's not like. This is our choo-choo train pulling out of the station, heading towards math lane. Woo-hoo. Multiplying decimals is a whole different ballgame than adding and subtracting. Remember, when we're adding and subtracting the like types of columns. Rules like that don't apply when it comes to multiplication. So if I have a number like this, a 44.7, and I multiply it by 0.642, this is the first thing I want to do. I want to get rid of those decimals. We're going to move them on out, and then we'll bring them back in during our final answer. So here what I do is I just count, and I say, okay, if I move this out, I would be moving it one spot. Because remember, to move it out, it has to be to the far right of a number. For the second number, to move this one out, I would be moving 3 spots. So now that I did that, moved it on out, I now have the problem of 447 times 642. Now just leave that off to the side for right now about how many spots you moved it. We'll come back to that in our final answer. Now we have to go through and actually do our multiplication. We need to remember how to multiply. We start here with the 2, and we're going to distribute or multiply the 2 to every digit in our first number. We take 2 times 7 and get the 14, put the 4 down and carry the 1. 2 times 4 is 8, plus 1 is 9. 2 times 4 is 8. Now we're not done, that was just multiplying one of our digits. We have several more digits to multiply. Now the next number, we start here with the 4. The 4 is in the tens spot. So when I take a tens number times a 1 number, I'm going to get a tens type of number. So I need to make sure that my answer goes in the tens column, which is your second digit. So you probably want to fill in a 0 here to make sure that you don't line it up flush to the right. 4 times 7 is 28, so you put the 8 down and carry the 2. Make sure when you carry, you are using the correct numbers. I like to use different colors to make sure that I don't accidentally use the 1 that I carried from my previous multiplication. Color code everything to make sure that it stands out in your head. 4 times 4 is 16, plus 2 is 18, so we put down the 8, carry the 1. We have another 16 plus 1 is now 17, making sure that we once again leave ourselves enough space to line up numbers underneath. Continuing on, we now start with the 6, which is in the hundreds spot. 100 times 1 would be 100. So our first digit will be in the hundreds spot. So now because I'm in the third digit over, I put down a 0 for the ones and a 0 for the tens spot. And now I can do my multiplication. 6 times 7 is 42. You put the 2 down, carry the 4. 6 times 4 is 24. Add the 4 is 28. Put the 8 down and carry the 2. 6 times 4 is still 24. Add 2 is 26. Now I've used every digit in the second number to multiply to every digit in the top number. So now we find our total, or the sum, which means we're going to add. So from the right to the left, we drop down, we have 4. 9 plus 8 is 17, carry the 1. 8 plus 8 is 16. 17, 18, 19. Carry the 1. 8 and 7 is 15, plus 1 is 16. Carry the 1. 6 plus 1 is 8, and the 2 comes down. Now, we're not quite done yet. We did some great multiplying there, but we need to remember that our beginning numbers were decimal numbers. So our answer is going to be a decimal number of some sort as well. Now remember, we had one spot that we moved the decimal point out for that first number, and we moved the decimal point 3 spots for the second number. That meant we moved a total of 4 decimal spots, which means that now the decimal is here at the right. We have to move it back in all of those spots. So from the right, I'm going to count in 1, 2, 3, 4, and that's where my decimal goes. So the final answer to this problem is 28.6974. Move the decimal point out in all of your numbers, find the total number, That's how many spots you move it in at the end. If you move it out here, you move it in at the end. Let's try one more of those to make sure that we have it down pat. Here I have 7.201 and I'm multiplying it by 5.48. When multiplying, the first thing you do is move the decimal points out. So I need to move this to the right, 1, 2, 3 spots. And I'm going to write down that I moved it 3 spots. And my next one, I moved it 1, 2 to get it out. So I'm recording that, 2 spots. So now the numbers I have, I'm multiplying 7,201, and I'm multiplying that by 548. And now I can do my multiplication like we all learned how to do. 8 times 1 is 8. 8 times 0 is 0. 8 times 2 is 16, so you put the 6 down and carry the 1. 8 times 7, remember it's 5, 6, 7, 8. So 56 is 7 times 8, but add 1, so that makes it 57. Now I start off with my tens digit, so that first number is going to go right here below that. If you need to, fill in the 0. 4 times 1 is 4. 4 times 0 is 0. Love it when zeros are in there. 4 times 2 is 8. And 4 times 7 is 28. Now we start with a 5. Once again, that's in the hundred spot, so that's going to go straight down here, which means I have 2 zeros I have to fill in first. 5 times 1 is 5. 5 times 0 is 0. 5 times 2 is 10, so we put a 0 down and carry a 1. 5 times 7, 5 times an odd number will end in an odd number, or 5. So that's 35 plus 1 makes it 36. And now we do a nice job of lining up our digits. Adding from right to left, we have an 8, a 4, 6 and 5 makes 11, carry the 1. 15 plus 1 is 16, carry the 1. 8 and 5 is 13, plus 1 is 14, carry. 6, 7, 8, 9, nothing to carry there, and the 3 comes down. And last but not least, we have to put in our decimal point. We had 3 moved out here, 2 moved out here, for a total of 5 spots. So from the right, we move in 5 spots. 1, 2, 3, 4, 5. So our final answer for this problem would be 39.46148. Now if you look at this problem, it kind of makes sense. This number, although it has several digits up here, is really 7 point something, so it's about a 7. This number, yeah, we got these decimals, but it's about 5. 7 times 5 is 35, so our number is going to be around 35. It's going to be larger than that because we have these other digits that are doing things for us. But our whole numbers should be about 35. Oh, we're at 39. That's pretty close. That lets us know that we must have moved in the right number of digits. If we had only moved in a couple of, 4 digits instead of 5, we would have had a number of 394. Does it make sense that 5 times 7 would be a number like 394? This is where we have to look at the problem and see if the answer makes sense. We're allowed to do that with the nice little whole numbers. We know that that's got to be about 35, give or take. Why do we call our pennies cents? Cent is a prefix that means 100. A century is 100 years. A centimeter, there's 100 centimeters in a meter, so it's 1/100th. So a cent is all about 100. So 100 pennies or cents makes a whole dollar. So cents are a fraction or a portion of the whole in our currency, which is dollars. So we write out numbers and we would say something like, oh, it had a price tag of $5.98. Now notice when we read it off, we said $5.98. The only time when you read off a number in Mathland that you use the word and is to indicate a decimal point. Okay? We do not say, oh, it was 103 degrees in the shade yesterday. That's incorrect. Saying 103 degrees would be saying 103/10 degrees. So we have to be very careful with our wording on things and how we talk about it. So it's 5 whole dollars, and then the fraction, which is out of 100, because remember it's 2 decimal places, so that's tenths and hundredths. That's why that represents our cents. Right. So if I had $5.98 and I wanted to find out, well, I happen to have $5.98 in a piggy bank jar, how many pennies or cents is that? How do I convert this dollar amount, which is a whole dollar and a portion or a fraction of a dollar, into just pennies or cents? And to do that, we simply move the decimal point 2 spots over to the right. So it's 598. Now we need to indicate that it's cents. We put our cent symbol after. Now this is another thing to notate. Right? In our currency, for whatever reason, we once again like to be a little bit different than every other country in the world. We put our dollar symbol, or the symbol for our currency, in front of our number. Even though we would say this is $5.98, we don't put the dollar symbol after. We start off our numbers always with the dollar symbol. However, if we use cents, that unit goes at the end. It's 598 cents, or pennies, that we have. So to go dollars to cents, you move your decimal place, move decimal point, 2 spots to the right. Which means then, of course, if I had 1,257 cents, to convert that into pennies, I move my decimal point 2 spots to, or from cents, if I move it to dollars, I move it 2 spots to the left. So to go from cents to dollars, we go to the left. And we put our dollar symbol in the front. So that'd be $12.57. Now it's very important that you know the difference between this. Because if you don't, it's like working at Walmart. I was shopping at Walmart for a bit, and there was a clearance bin. Oh, fantastic. And in this clearance bin, you know how they have their little signs out there? The stuff in here, oh, that's clearance. And I said 0.25 cents. So I grabbed 4 of them and a penny, and I went up to the cash register. And they said, it comes out to $1.06. I'm like, no, it's a penny. I was nice. I bought 4 of them so that you didn't have to break change, because a penny is our smallest currency. We can't go any smaller than that. We can't break that up. And of course the cashier looked at me like I was, what? The register says it's $1.06. I'm like, no. Your bin said that it was 0.25 pennies. So it's 1/4 of a cent for 1. She got really confused and didn't know what to do with that. The machine says, I don't care, the bin was labeled incorrectly. You do not have a decimal point when you're talking about cents. Cent is the smallest unit that we can have in our currency. You can't go any smaller than a penny. Can't break it in half. So you're not going to have a portion. Remember, a decimal is a portion of a whole. You're not going to have the decimal point with your cent symbol. The sign should have read one of two ways. It could have been written as 25 cents, or if we were talking with our dollars, it would be a quarter or a fraction, 0.25 of a dollar. So be very careful about your notation. You don't want to be Walmart. All right, so just like with everything else, we can also solve equations. This is an equation because it has an equal sign. When it has an equal sign, we're not trying to simplify, we're trying to get it balanced. This is a true statement. We're trying to get it balanced so that my variable is all by itself on this side, and as long as I am still balanced, then its value, what it's worth, that unknown that we're trying to find, is on the other side. And so then we can find the value of that unknown. Now I'm going to review a couple problems that we've already done, two-step equations. These have some decimals in it. And then we're going to go on and say, well, what happens if it's beyond a two-step equation? And we have some other things going on. How do we solve those equations? So we're definitely moving up for the difficulty of solving linear equations. So in this problem, we still just have our two-step. We have 6 times x plus the 7.4 is equal to 11. So the first thing we have to do is get the term that has my variable all by itself. So the term here, the constant, there's another constant over here. We have to get those together. Now they're on opposite sides of the equal sign right now, so we have to do an inverse operation to cancel it out or to move it on over. Since I'm adding 7.4, if I was adding something on this side, to get rid of it, I would take it off or subtract. Well, if I subtract on one side, I have to do the same thing to the other side. So I'm going to subtract 7.4 and do the same thing on the other side. Now I'm subtracting a decimal. We need to remember that our decimal points for adding or subtracting have to be lined up. On the 11 over here, the decimal point is after it. So I have to line up my 7.4 that I'm subtracting underneath the proper positioning. The 6x comes along for the ride. The 7.4's cancel out is equal to, now once again, I cannot take 4 away from a blank space. There's a 0 up there. I can't take 4 away from nothing. This is 0, take away 4. I can't do that, so I'm going to have to borrow so that I now have a 10 that I can take 4 away from. The decimal point will be lined up so it keeps coming down. And then we have 10 minus 7, which is 3. So the first step is always adding or subtracting. In a two-step problem, the first step is always to add or subtract. And then our last step is to separate the number from the letter. Now the number and the letter being mushed together like that means multiplication. To cancel out multiplication, we divide. Whatever I do to one side, I once again do to the other side. 6 over 6 cancels out. I'm left with x is equal to 3.6 divided by 6 gives us 0.6. Now, I'm a firm believer that the reason that calculators were invented is to do division of decimals for us. Okay? So as long as you are showing that is 3.6 divided by 6, and that's the operation that you're doing, I don't need to see the actual long division. Feel free to plug and chug that into your handy dandy to come up with your answer. But you must show me that that's what you're doing. I'm taking this and I'm dividing it. Not just magically, oh, the answer is. Show me what you're doing, then you can use the tool to do that operation for you. And that's our final answer for this one. The value of x is equal to 0.6. Oh, do I need to have the 0 in front of that? If you want to help you see it, you can put the 0 in front, but it's not necessary. Let's do another. Here we have decimals in all of our terms. It's 0.2 minus 0.1x is equal to 1.4. The same rules apply though. We have 2 terms up there that don't have a variable and 1 term that does. We want to get the two terms that don't have a variable together. We gather the like things, and we want to get it away from the term that it's not like. So we want to move the 0.2 onto the right side. It's a positive 0.2 because, once again, the sign in front of the term goes with the term. So I'm going to subtract 0.2. Once again, zeros are optional. I just used it to make sure that we could see all of our digits and that we didn't lose the decimal point in front of it. Whatever I do to one side, I do the same thing to the other side. That cancels out. Now be careful when you bring down your variable term. The sign in front goes with. This subtraction was really adding a negative. So this term is negative. It has to stay negative as we haven't done anything with that negative yet. So the first step is always adding or subtracting, and then our second step, once again, is always going to be to divide. What do we divide by? We always divide by the number in front of x. The entire thing, sign included, because dividing a negative divided by a negative, two of the same thing, is a good thing, which means that my result will be positive on the left side. Only the number in front of x to get x by itself. Positive divided by a negative will give me a negative, and 1.2 divided by a 0.1 ends up with good old 12 for your answer. So that's reviewing our two-step problems. Now, sometimes we're going to have variable terms on both sides of the equal sign. So we're going to have to do another step. Let's try one of those. So here we have 10x minus 3 is equal to 4x plus 18. Now, I do believe that your book recommends that you move your constant values first. I don't agree with that. I want to put all my variable terms together first because I want to control whether the number in front of that variable is positive or negative. If I can make sure that it's positive, then I don't have to worry about that boo-boo mistake that we have the tendency to make later when we lose the negative when we divide. So I see that I have 10 x's on this side. On the other side, I have 4 x's. Because they're on opposite sides of the equal sign, I have to switch their sign to get them together. Remember, we're still moving the term. I'm moving the 4 and the x together. That's a term. Whenever you add or subtract, or whenever you're moving terms, you'll always add or subtract it. So I want to put this term, which is smaller, because 4 is smaller than 10, I want to put the smaller one towards the larger one. That'll keep my coefficient, or that number in front, positive. It's a positive 4x here, so because I'm moving the entire thing, I'm going to subtract 4x. Remember, I'm moving the term. I'm not separating the number from the letter. I'm moving the entire quantity, and that's why we always add or subtract. That's going to give me 6x minus 3 is equal to 18. And now we're back to having a two-step problem like we did previously. So our next step is to get the constant values on the same side. So in order to do that, I need to move this 3. The 3 is negative, so I do the opposite of that, which is to add or make it a positive 3. And then we simplify that. The 3's cancel out, which is the point of doing it. 18 plus 3 gives us 21. And once again, our final step is to now separate the number from the letter. When we separate the number from the letter, that's when we are dividing. So I divide both sides by 6. Just the 6. The 6 is canceled, leaving me with just the x. Now, this is the chapter on decimals, so I guess that means that you could divide this. However, in algebra, the rule is if your original problem does not have a decimal, you do not make a decimal here. This would be a reduced fraction. And yes, you leave it as an improper fraction, no mixed numbers in algebra. So when you're solving, you will not have a mixed number. I would have reduced this top and bottom by 3 and ended up with 7 halves. Because this is the chapter on decimals, I will accept this week and this week only you actually dividing it and coming up with 3.5 for your answer. I would prefer to see the improper fraction. But I do understand this is the chapter on decimals, so you might have divided it out. But as a rule of thumb, in algebra, if there's no decimal in the original problem, and they don't ask for a decimal approximation, you do not give a decimal answer. It's always a reduced fraction of some sort. Let's do another. Here's another example that has decimals, so our answer will have a decimal result. We have lots of decimals going throughout, but we're going to do this problem the same way as we did the others. We have a term with a variable here, we have a term with a variable on this side. They're on opposite sides of the equal sign, so we need to cross the bridge, and that means we do the inverse operation. Now I want to keep things positive. I notice that I have a 17 on this side and only a 2 on this side. The 2.1 is smaller than the 17.3. I always want to move my smaller term to the larger term to make sure that that number stays positive. So instead of moving it to the left side, I know we're used to seeing our variable always on the left, but it doesn't have to be. So instead of moving it to the left side, I'm going to move the 2.1 to the right side. Now it's a positive 2.1 because there's nothing in front of it, so that means I'm going to subtract 2.1x. The variable goes with because I'm moving that entire term, and now I line up my decimal points very nice and neatly and my like terms. Our result over here, don't lose the fact that the 45.3 is negative, so it's a negative 45.3 is equal to, subtract this off, we end up with 15.2x, and then add the 23.1 at the end. Now I'm back to that two-step problem, so now I want to move this constant of 23.1 from the right side to the left. Now in order to move this, it's positive, so I'm going to switch signs. So I have to subtract. When we do this second step, we do not have the choice of making sure something stays positive or negative. Because my variable term is on this right side, the constant has to go on the left side. So I have to move the 23.1. I do not have a choice anymore. But I would rather have this number be negative than try to remember to divide by a negative in my next step. Both numbers are negative, so we add the numbers and keep the negative. 15.2x comes down, and the 23.1 cancels out, which was our purpose or our goal in that step. And now we need to get the variable alone. We're not just dividing by the number that's over here. You always divide by the number that's in front of your variable. So the 15.2 times x is the 15.2 is what we need to get rid of. So I divide both sides by 15.2. You do not make the x go with it here because we are dividing. We're separating the number from the letter. And whatever you do on one side, you do on the other side as well. That cancels out, leaving us with x all by itself on that side. And once again, on this side, division is when we can use our calculators. We see that this is a division. Type it in your calculator the way you see it. It's the top number divided by the bottom number. A negative divided by a positive will give me a negative. And when we divide that out, I do believe we get 4.5. It's okay to have your answer with the variable after, as opposed to the variable first and then the number. I call this Yoda talk. Instead of saying x is negative 4.5, negative 4.5 is x. Good he is. Remember, Yoda always said things backwards. And that's okay. It's acceptable. Let's try another with another little twist to it. Now this problem is a little bit different than our last ones. If you notice, we have parentheses in this problem. Parentheses are there for a reason. If we look at it, we have a number that's in front of the parentheses. That indicates multiplication. So to actually do our multiplication, this is called that distributive property or the distributive law. We need to take the 3 and multiply it to every term inside. Well, wait a second, I thought we were supposed to simplify parentheses. Yes, but I don't have like terms in here. I cannot add 5 to x if I don't know what x is. Adding 5 is not the same thing as writing it as 5x. 5x means multiplication. Multiplying by 5 is not the same thing as adding 5. So keep that in mind. So in order to get rid of my parentheses, I'm going to use the distributive property, taking the 3 and multiplying it to every term inside the parentheses. That's cleaning this up and is going to give me 3x plus 15. And I didn't do anything on the other side, so it just comes along for the ride. Now I have a problem just like the last one. I have variable terms on both sides. I have constant terms on both sides. So our next step is to get our variable terms together. Once again, I want to keep them positive. Here I have 3x. Here I have negative what? What's there? Oh, I don't have any. Yes, you do. Because if it was a 0, what's 0 times x? 0 times anything is 0. There's got to be a number there. Ah, the god of Mathland, he, she, it is always with us. We're subtracting 1x. Well, a negative 1 is smaller than a positive, always. So I'm going to move that term to the left side. It's a negative 1x, so I'm going to add the 1x. If you need to put the 1 in to remind you that it's there, do so. Whatever you do to one side, you do the exact same thing to the other side. So 3x plus 1x makes it 4x. Plus our 15 is equal to 20. Now we're back to our two-step problem. So now we move the constant to the other side away from the variable. The variable's on the left side, so I have to move this over to the right side. It's a positive 15, so we're going to subtract 15. Once again, do the same thing to both sides. Bring it on down. We got our 4x. The 15s cancel, as they should. Our goal is to get the number on one, or the variable on one side, the number on the other. Subtracting, we get 5. And then, as we did before, the last step is to divide by the number that's in front of x. So we're going to divide by 4. So our answer is x is equal to, once again, for most algebra problems, I would leave it as 5/4. Am I running off the screen? X is equal to 5/4 is how I would like to see the answer. This week and this week only, if you divide it out, I guess I will accept x is equal to 1.25. Okay. But practice leaving it as improper fractions. So in this step, we had an extra step first that we had to get rid of parentheses. Maybe we should try one more like that. Now in this final example, it's very similar to the last one. We had those parentheses, but there's an extra step that we're going to have to complete in this one. Because after we distribute through, we have to do something with this minus 15 as well. But the first thing I see is parentheses. So whenever you see parentheses, the first thing you should think about is let's get rid of those by using our distributive property. So I'm going to take the 8 and multiply it inside to both terms. That's going to give me an 8x minus, because positive times the negative stays negative, 16. And then I still have this minus 15 is equal to the 4x plus 2. I did not take the 8 times the 15 because the 15 is not in parentheses. I only distribute the 8 inside the parentheses. At this step, though, I notice that now after having multiplied, I have some like terms on the same side of the equal sign. So I want to gather these together to make as few terms as possible. So as these are both constants, they're on the same side of the equal sign, so we do not switch signs. We just simply say, I have a negative 16 and a negative 15. They are both negative, so we add them and keep the sign. So that's going to give me 8x minus 31 is equal to 4x plus 2. So I just cleaned it up by combining my like terms. I did not move it to the other side of the equal sign, so we do not switch signs. Now I'm gathering my like variable terms. Here's an 8x, on the other side is a 4x. I want to get those together, and so I'm going to move the smaller 4x to the 8x. Because I'm going from one side of the equal sign to the other, now I switch the sign. This is a positive 4x, so I'm going to take away 4x and do the same thing on the other side. That's going to leave me with a 4x minus 31 is equal to 2. Now we move the constant terms together. I have a negative 31. I need to move that to the right side. I'm crossing the equal sign, so we switch signs. So we're going to add 31. And once again, whatever I do to one side, I do the same thing to the other side. That leaves me with 4x is equal to 33. Running out of room, so I'll rewrite that up here. 4x is equal to 33. Now we're ready for our last step. Our last step, once again, would be to get rid of that 4 in front of the x. So we're going to divide both sides by 4. 4's canceled there, leaving just the x. Once again, on the right side, this is a reduced improper fraction, so I would love to keep that answer like that. Less work. You just have to make sure it's reduced. But since this is the chapter on decimals, if you want to go to the calculator, you can, but that's more work. Here, the answer's right there. But like I said, if you want to go to the calculator, 4 goes into 33 8 times with a quarter left over, so it's 8.25. Would be accepted this week as well. So solving equations, if you have parentheses, you have to distribute through to get rid of them. If that causes you to have like terms, add them the way they are. Then move your variable terms together from one side to the other. I always take the smaller, move it to the side with the larger so that I can keep it positive. Then you don't have a choice. For your constant value, you have to move the value that's next to the variable to the other side. And last but not least, divide both sides by the number in front of x to get your variable alone. So now we have x is equal to and its value on the other side. We've solved for that unknown.